have not necessarily this order, Newshaw Bahreyni, Kenyon College, Kevin Knuth at the University of what is it? SUNY Albany, yes, and James Lyons Walsh at SUNY Albany as well. So please.
Well, thank you very much. I want to thank the organizers, and thank you, David, for giving us this opportunity. This is going to be kind of a tag team talk. We had sent in 3 abstracts, and they were related to each other, and the organizers thought that we should all kind of be teamed together, and so this is the result. So we're going to talk about a theory that we've been working on. It's very different from what we've seen in the past. It's inspired by the causal set theory, but to kind of dispel any notions of expectations, I'm going to start with a slide with a quote from one of our reviewers. And this is a review from one of our papers that's published in Contemporary Physics. There's very little conventional physics in the paper. I can't say that I understand it or its relation to ordinary physics, although most of the key elements in ordinary physics are claimed to be embraced. It is really a lengthy sketch of an alternative approach to the scientific that is carefully ordered and self-consistent description and interpretation of the So I thought that was a very interesting reviewer comment. And it's not wrong. So we're basically decided to start from scratch, start all over again, and think about coming up with a different set of postulates to begin. It was initially inspired by the work proposed in causal set theory, Raphael Sorkin, Lobelli, Dauter, Jensen, Reed, and however, it relies on a partially ordered set of events. However, as we'll see, we take a different turn. So we don't call them causal sets. I call them sets, partially ordered sets, because I don't want to have any confusion there. And we've also been calling it the influence network. So we don't consider concepts such as space-time, mass, energy, momentum, motion, force to be fundamental in any sense. Our goal is admittedly ambitious. Why not? Right? We only live once. Let's try to derive it all right from scratch. All right. Well, let's be a little more cautious. A more cautious attitude is reflected by the idea that what we're going to do is we're going to start with a very simple set of postulates and see how much you can derive. If you can derive even a few interesting things, that should give you some insights into what a foundational theory might look like. So central to our efforts is this concept of symmetry constraint or consistent quantification. And when I talk about symmetries, I'm not going to talk about symmetries like supersymmetry or symmetries that come about from conservation laws, because I'm not treating any of these as fundamental. We're talking about even more basic symmetries, associativity, commutivity, things like this. Some of this is actually described in my current FQXI essay, so you can look at that there. So we're going to start over. So many of us feel that we've experienced electrons directly, whether it's a crash and a bang of a lightning strike in a thunderstorm, or whether a little shock that you give your little brother or sister by rubbing your feet on the carpet in winter. These seem to be bright, crackly sorts of things, right? But what are they really? This is the question. If we understood the electron, so imagine that they might be pink and fuzzy, or maybe they smell like watermelon, something ridiculous like this. The idea is that whatever properties or attributes an electron may possess, you can only know about such qualities if they affect how an electron interacts with you or your equipment. So if the watermelon smell of an electron does not influence or does not affect how it influences your equipment, you can never know about the watermelon smell of the electron, right? So let's back up a little bit more and then consider what properties you can know. So the only properties that you can know are those that affect how an electron influences others. So we're going to take an operational viewpoint. We're going to define an electron. We're can define electron properties based on how they influence others. So influence is going to be central to this. So since we can't know what an electron is, perhaps it's best just to simply focus on what an electron does. So here's a nice quote to set the stage from Bertrand Russell. The observer, when he seems to himself to be observing a stone, is really, if this existed with belief, observing the effects of the stone upon himself. This kind of embodies that sentiment. So we're going to assume that there are things in the universe. You have to assume something, right? So there are things. I don't know what they are. Objects, entities, particles, whatever you want to call them. We're going to focus on the word particles. And we're going to assume that all we can know about these things is that they influence one another. Right? So we're going to really strip it down as much as possible. I don't know what the influence is like. I don't know what's mediated. I don't know whether it happens in space or not. I can't know that. I can only know I was influenced. So,
but what does influence mean?
it influenced you. I don't.
Did it change an internal property in myself?
Right. It could be something like that. So
what are those basic properties that things have?
So that's a good point. So in this paper here, this one here, actually I'll address that in a moment. So we're going to consider that things can influence each other, and such influence is directed. So an active influence and the act of being influenced are both considered to be events. So we're going to take this as a way to think about events. So events are going to occur in pairs. If I poke James, I have one event is the act of me poking him, and the other event is the act of him being poked. Each event is associated with a different object, and the asymmetry of influence allows these two to be ordered in some way. So there's some detail that I'm going to skip out, and it's related to your question. The idea is that we're going to represent a particle or an object as a totally ordered sequence of events. And so to actually get this total order, one of the ways that we had come up with to do this is to assume that there is some kind of internal state, and that this internal state somehow changes when a particle is influenced or influences, but we don't have access to it. We don't actually need to know what that internal state is to be able to actually perform such an ordering. So here we're going to model a particle or an object as a sequence, a totally ordered sequence of events. This object can influence other objects, so each event is actually coupled to another event on another object. An observer is going to be assumed to have some kind of detector, and he can actually monitor a particle. Okay, so we'll sometimes call these observers. And so this will be the particle that the scientist is looking at or focusing on. So to clean the diagrams up, I'm going to remove arrows, straighten up chains, and we'll have a nice partially ordered set like this. Now the other important thing is this while the ordering is directed here, it's like any O set, you can actually swap the ordering. The ordering is arbitrary, so you can flip it upside down. So we basically have a partially ordered set, and we assume that influence is transitive. That's another assumption. So another thing that another procedure that we will employ is coarse-graining. We'll imagine that maybe your detector isn't good enough to observe every single event, so you can't distinguish between these two, and such coarse-graining can actually change the connectivity of the post site, right? So the connectivity that you observe actually depends on your ability to resolve events. So now we're going to talk, oh yes?
That might result in not being partially ordered anymore. Take your two ovals in the middle. Imagine that we're an X between the lower and upper dot on each side.
Here?
The two ovals.
These two ovals, yeah.
Yeah, so lower dot on one connected to the upper dot on the other.
Right here?
And then the other way as well.
Okay.
And then compress the ovals.
Oh, all right, yes, so then it's not partially ordered.
Yes.
Oh, that's a good point. Okay. All right, oh, we'll have to see if that causes any trouble. Thank you. I don't think it'll cause any trouble for the later assumptions that we have. All right, now comes the idea of quantification. We're going to follow Galileo here. Measure that which is measurable, and make measurable that which is not so. Very wise. So let's do that. So the idea is that we're going to somehow quantify this partially ordered set of events. Now, partially ordered, I don't know what kind of variety we could get, right? So where do you start? Well, one of the ways we could start is let's just focus on the single particle chain. This is easy, it's totally ordered. So any monotonic valuation that basically encodes the total order is isomorphic to just counting. So I might as well label them 1, 2, 3, 4, 5, 6, 7. So we're going to assign to each of these events along the particle chain a number that increases as I go up the total order. Forget that I have this thing. Now the question is, how do we quantify the rest of this partially ordered set, or some of it? Maybe you can't quantify all of it. The idea is that this theory is going to be observer-centric. We're going to focus on how the observer perceives the network. So we're not going to have a God's eye view. Question is, the scientist is monitoring this particle. What does that tell you about the partially ordered set? So you can observe that there are different ways. There are 4 different ways that an event not on the particle chain can affect the particle. They could be totally incomparable. There could be an event that eventually, through the partially ordered set, influences an event on the particle chain. And so we define, we call this a forward projection. We define the forward projection as being the least element on the particle chain that's influenced by this event. You can go the other way. There could be an event that is influenced by the particle. And so the back projection, which means a bar, is defined as the greatest event along the particle chain that influences that event x. And you could have it so that both occur, so the particle chain influences that event, and that event in turn influences the particle at some point. We're going to actually focus on this situation, because this is more rich. I'll show you what happens. We can treat this here as a label for this event, so I'm going to call this event little piece of x. This capital P you can think of as an operator that maps, that projects that event x onto the particle chain. So we often use this operator is usually named after the chain. So quantification can be extended by relating these poset elements to the embedded chain via this concept of chain projection. So for an element x, there's the potential to be quantified by a pair of numbers. So whatever these numbers are along here, I have the potential to assign 2 numbers to each event in the partially ordered set. So here is how this observer chain or particle chain would quantify this network. So here's an event. It's labeled 5, 1. It forward projects to the particle chain at 5. And if I back project, it projects to 1. So it ends up giving you a kind of a bizarre coordinate system. Now, not everything can be quantified with 2 numbers. This event, for instance, is not influenced by any event on this finite particle chain, so it gets a dot. This one neither influences the particle chain nor is influenced by it. So there are some aspects of this partially ordered set that can't be quantified this way. We're going to focus on the ones that can be. Okay? And see what happens. So I'm going to have a short intermission. If there's a question or two, clarification question or two, we'll do that, and then I'll let Newshaw take over. Yeah.
So is I'm sorry, you probably said this, but is the particle associated with the chain then, and not the events?
The particle's represented by the chain of events.
Right.
Thank you.
Any assumptions about countability or
I'm
finite?
sorry?
Are you making any assumptions about finiteness or?
Yeah, we assume that's all finite. It's all finite. Finite chains, finite.
Why would nodes get unique coordinates?
I'm sorry?
I mean, why couldn't two nodes have the same coordinate in this scheme?
Oh, they can.
Okay.
Two nodes can have the same coordinates, yeah. I don't know, they might have, if you go back, see if there's one that does. I don't know if I put one in the picture that does.
But there might be, it's not.
No, yeah, it can happen though, yeah.
They're not exactly coordinates.
No, they're not exactly coordinates, yeah. Yeah, it's kind of a bizarre quantification line, right?
Okay, so, so I'm going to talk a little bit more about what else we can infer by just this very simplified picture of events and their influencing one another. We can look at the order of influence. So we can say that, for example, two chains, these are, for example, two chains, and then this is an event inside the poset. And I can talk about the projections of this event onto these two chains. And if the projection of this event X onto the two chains P and Q is such that its projection onto one is first found on the other one, then I call the two chains in this one event collinear. And I can interchange the P and Q and I still can have that condition. Now, these are not in space, these are actually nowhere, it's just a set of events and their relation with respect to one another. The way that is drawn this way is just to show you the more simplified picture, but what I'm looking at is the order in the influence, and that is all that matters. So for example, here, this event X, if you look at this event on chain Q, that tells me that this event X is projected onto Q, but it's first projected onto chain P for the forward projection. And this one, for example, tells me that the backward projection of event X onto chain Q is first found on chain P. So that tells me the order in the forward and backward projections. And you can also see that here. Yes?
Are those lengths just the influence arrows?
Yes, yes, yes. And we got rid of the arrows later, previously.
And what happens if there's more than one way of reaching it from?
One way of reaching.
So if there's another event that can, if you can sort of project it through multiple events, or is that not possible? So if you have like another node.
Another event here, and it's projected onto the two chains again? Is that what you mean?
Well, the projections are the least, the greatest depends on the chain.
Yes, so we defined earlier that the projections are the least of the greatest. Yeah, okay. All right. So I can have another condition by just this ordering, and although I said that these are not in space and time, I'm just drawing these this way so that it makes clear what I mean by the directionality. So the ordering projection can tell me whether an event X, in addition to being collinear with P and Q, might be on the left of the two chains P and Q, or it might be in between the two chains, or on the right of P and Q. And they do not necessarily need to look like that. I just can follow the ordering projection of X onto these two chains, and by following that order, I can, if, for example, if in this case, the projection of, which is what you saw previously, if the projection of event X onto chain Q is first found on chain P, then I say, for both forward and backward projections, then I say, well, X is on the left. But that's just a more simplified picture. I just want to clarify the fact that they are not nowhere in, there is no space, there's nothing, it's just the order in relation. Yes?
Why not just say X is closer to P than to Q?
Closer to, well, I want directionality. That gives me much more information to say whether it's on the right of X or left, right of P or left, or in between the two. It can be in between the two. How can you say whether this is closer to P or this?
I don't want to say that, so I would be
But that
happy,
gives
I'd be
you-
happy if you just stuck with between this as your relation here rather than left and right.
Well, because this gives you an additional information to define another a notion, which I'm going to get into in the next slide. So it matters that it's, and we also consider an event which quantifying the event with respect to these two, in this case, not in these two cases later on. So that's an additional.
I was just going to add that with the algebraic relations, there's 3 equivalence classes.
Yeah.
So there's 3 different classes, and each corresponding to different each class.
Yeah, so these are.
Just objecting to the name, because left and right sort of implies that there's, a one-dimensional
And I just.
thing in the picture, which there isn't. So.
And then there is also one thing that everything that we are, most of the things that we are presenting in this theory is just derivation. So for example, this alone is like 3 or 4 pages of derivation of getting from different equivalence classes down to like 3 of these, because we have nothing that we can use from the ordinary physics or anything that we are familiar with.
Although he's worried about this giving you 1 dimension, but it does.
It does.
It's an induced 1-dimensional space because of this additional ordering that comes about from the algebraic relations.
Yeah.
So it's an induced ordering that comes from the chain projections.
Yes.
Sure, I can give an example where it's not, but that's related.
There's something intrinsically 2-dimensional in here?
It's just because of the chain projections, it allows you to order x, p, and q. So as long as a projection from x onto one of the chains can be found by projecting it either forward or backward onto the other chain and then back to the other chain, that allows you to define an ordering of x, p, and dx. And once you can define that, you can define a 1-dimensional subspace in the partial orders.
This might help.
In that situation.
This might help in seeing an example where your projection onto, for example, this chain Q is not the same as the back. It cannot be found as a back projection on chain P. So, for example, if I follow this projection onto chain Q, it is the backward projection of X onto chain P. But look here, if this is the forward projection of event X onto chain Q, the backward projection is not the same as that. So you see that this is the backward projection, and it does not lie inside the 1-dimensional space that is defined by that. And that's what gives me the discrete subspace. If that is the case, then I can define a discrete subspace defined by the 2 chains P and Q where X resides in it. But this one is not, X does not reside in the discrete subspace that is defined by the 2 chains P and Q. Okay. I can also talk about 2 chains. So if 1 chain can give me that much information, and I can already quantify the poset with 1 chain, but having 2 chains is a stronger constraint that results in many more interesting results. So I'm going to, if I have 2 chains inside the poset P and Q, such that any interval, any pair of events project onto the same pair of events on the other one, both forward projection and backward projection, such that this relation, this equation actually holds between the forward and backward projections. Then I call these 2 chains coordinated. So for example, here the interval on chain P that is defined by these 2 events, that is delta P, has the length delta P, is forward projected onto chain Q and backward projected onto delta Q bar, and such that these delta P, delta Q, delta Q bar are the same. So if that happens, then I call the 2 chains coordinated. And I can talk about the length of this interval by that is given by this relation delta P plus delta Q divided by 2. This is kind of obvious because if delta P and delta Q are the same, then I can as well get the length of this interval by adding them up. derivations of all that we've done so far. Okay. I can also talk about the relation between the two chains. Now remember, I'm not talking about any space, or these do not exist in any kind of space, but I'm just talking about the relations between the events and the chains inside a coset by means of influence. That's all I have. So I can talk about the relation between chain P and chain Q, coordinated chains P and Q, such that if you take a look at this interval AB, this directed interval AB, it forward projects onto delta Q, which is minus Q, and it backward projects onto, it projects onto chain P by length 2. So if this relation here gives me the distance between the two chains. Now, by distance, I mean only the relation between the two, but I call them distance. And it is actually derived based on the fact that the choice of events on the two intervals should not actually matter in giving you the directed distance between those two chains. So, for example, if you look at this interval, AB, then delta P is 2 minus 2 gives you 2, divided by 2 gives you 2, and it's the same as that. So clearly the choice of events on two chains shouldn't matter. Okay, I can also talk about, so far I have the length along the coordinated chains, I have the distance between the two, which is the relation between the two coordinated chains. And I can also, I need another scalar, or something that remains invariant. And there is a very important and a very long derivation that gives you this quantification, which is the scalar quantification, and comes from the scaling between chains that do not, intervals on one do not project onto the intervals on the same length. So in other words, between two chains that are not coordinated. So if you consider that very general case, you will get the scalar actually quantification given by delta P times delta Q. Now, if you look at this general interval here, and I can rewrite the quantification for this guy in terms of the distance, the directed distance between the two chains, and the length between the two chains, which in terms of delta P and delta Q translates into this equation. And this is nothing but this delta S squared. So this is the scalar quantification in terms of the length and the distance between the two coordinated chains. So here's a very nice quote from John Wheeler: individual events beyond law, events so numerous and so uncoordinated that bonding, they are freedom from formula, they yet fabricate firm form. All right, so now let's focus on different types of intervals that we can have. Now, this picture, I so far talked about a pair of coordinated chains that quantify intervals. You can do the same thing instead of projecting onto two coordinated chains. I'm forward projecting this interval onto this chain and backward projecting it. So I can still have the same type of quantification scheme that I talked about with respect to one chain as well. Nothing changes. These are the three types of examples that can happen for intervals that are quantified, for example, by this chain inside the coset. If you look at this interval here, you can project this interval onto 5 and 6, onto this interval here on the chain, and backward project it onto this interval. So therefore, your interval can be quantified by 4 numbers, which are 5, 5, that is this guy here, and then 6, 4, which are the forward and backward projections onto the chain. Now I can quantify, equivalently I can quantify that interval by a pair of numbers, which is when you subtract the 2 pairs here, 5 minus 6, or 6 minus 5, sorry, and 4 minus 5. So you get a pair that quantifies that interval. Or you can use the scalar quantification formula that we just we derived that I showed you in the previous slide. We didn't derive it here, because it's a lot of work. But anyway, so the scalar is given by the product of the two elements of this pair. So there are 3 ways that you can quantify this interval. Now, this is an example of an anti-chain-like interval, and you get the scalar to be a negative number. You can look at this interval, which is, and then find the 4 tuple, the pair quantification, and the scalar, which gives you 0, and that tells me that this is a projection-like interval when one of the elements of the quantifying pair is 0. And if both of them are positive, which gives you a positive scalar, then you have a chain-like interval. So these are the 3 different types of intervals that you can have. Now, I can look at 2 sets of coordinated chains such that they are not all coordinated. They are coordinated pairwise, but not all of them coordinated with one another. So for example, here, P and Q are coordinated with each other, and P prime and Q prime are also coordinated, but PQ is not coordinated with P prime and Q prime. And look at the relation between the quantification pair that I get from quantifying this interval I, general interval right there, with respect to each of these pairs of quantifying chains. So if I do that, then I can derive this equation that gives me the relation between the quantifying pairs with respect to P prime, Q prime, in terms of the pair that is given by PQ. And you can see that there's a factor of square root of m divided by n, where your m and n are the projections of an interval on PQ onto P prime and Q prime. Okay, now let's put everything together. So far we had the length along the chains, the distance between the two, and I wrote down the pair quantification of any interval that is quantifiable by a pair of chains, coordinated chains, in terms of these 2 guys. And I also wrote down the scalar quantification of the interval with respect to these 2 guys, in terms of these 2 guys here. Now, I can go ahead and rename this to be delta t, and this guy to be delta x, and look what I get. This scalar quantification becomes my Minkowski metric, which is basically nothing but just a relation between the events and the chain, and consistently quantifying it. And I can go ahead and define a very useful quantity data as delta x divided by delta t. So I get that. Remember, there is nothing is moving. This is just a partially ordered set with relation between events and chains that are quantifying them. So all that is just a relation between them. That is only that. But it turns out that that is a very useful quantity, and that it's bounded. So there is an upper and lower bound, so we can get plus minus 1, which is equivalent, or 0. And in the case where delta p equals delta q, which makes sense because that means that you have your, both of the chains are quantified with the same thing. Okay, and I can also define this gamma to be 1 over 1 minus beta squared square root. And if I make use of these, and I again take a look at this interval that is quantified by PQ and P prime and Q prime and their relation, I can go ahead, rewrite each of these guys in terms of delta x and delta t. And if you solve for delta t prime and delta x prime, that is what you end up with, which is the Lorentz transformations. And this is another amazing result from just influencing, and I'm not adding anything to the picture. Remember, I don't even have space or time. I just renamed the relation between the two chains, coordinated chains, to be my delta x, and the length along each quantifying chain to be my delta t. That doesn't mean that I have space and time. I just renamed those and just came right out. And I'm gonna, if there are any questions, yes.
I just wanted to remark that perhaps the fact that you get back the structure of Minkowski space in a sense, or something that looks very much like it anyway, may not be quite as surprising as you thought it was, because it's been known for a while that, people like Rob, for instance, have, I think in the 1910s, already produced derivations of the Minkowski, the geometry of Minkowski space-time based on something like an influencing or causal relation and some basic assumptions about what it does. So perhaps that's just another instance of a derivation in that sort of general family.
Yeah.
So you said there's nothing, you didn't put anything in other than the sort of influences, but that, if I understand what's going on, right, that doesn't seem quite right, because you had to do the coarse-graining as well, right? That's putting something pretty substantive into this. Can you say more about what you just sort of drew some pictures around things. What are the constraints on the coarse-graining?
So basically what gives us this Minkowski metric and the Lorentz transformation is the fact that each event can be influenced and can influence. But you will see that that is not the case in the quantum picture. So in the particle picture, it is either being influenced or influencing.
It's coordination.
Yes, and then it's the coordination that gives you the, coordination is actually the most important.
These are two total orders. I mean, they're a pair of inertial particles, and you're checking off seconds of proper time along them, right? And then you're putting in the light currents.
So it's exactly a coordinate system in 2 dimensions. It's obvious that it's going to give Minkowski fields. There's nothing surprising about it at all.
Yeah, the coordination condition is critical. That's the assumption. And as long as you have that coordination condition.
Yes.
Can I ask, is every maximal chain a particle, or a particle a special subclass of the maximal chains?
Can you say that again?
So when the notion of a particle was first introduced, was it claimed that any maximal chain counts as a particle, or are they a special subclass of?
No, nothing special.
So they never used the word maximum. So their chains, although everyone they drew was maximal, they never said that that had to be the case. I think they mean that it does.
So I guess what I'm thinking is that thinking in Minkowski space-time terms, I can have arbitrarily accelerating particles. And it would be funny if I got the Lorentz transformations out from quantizations with respect to those.
Accelerating.
Well, relative, so if I start off with my inertial particles, and then I just, there's a causal influence from one to the other, so I go up one and then I go along that influence and then up another. So that seems to be a particle in your definition. And so now I pick some of those which are sort of accelerating.
I said I'm talking about the coordinated chains. So if the two quantifying chains are coordinated, the length along each that you're going to measure is going to remain the same. So that's not going to change.
So they're like co-moving observers. But now I'm considering two coordinated chains which are not co-moving relative to my, are not uniformly moving relative to my first set. They seem to be allowed by your framework.
Well, maybe I can go back to where I introduced that. So if you go back when we first introduced the notion of influence, this, for instance, isn't a particle chain.
Why not?
Because the idea is that the particle chain is and you brought up the notion of states, that you've got some kind of ordering of states and ordering of events along the particle chain. And the particle chains are connected in such a way that each event is defined by an interaction with only one other particle chain. So it's a very specific connectivity between the chains. So not every chain of set is a particle. Such that that's the
Right.
And then the idea is when you coarse grain this, the assumptions that lead to Minkowski are that you coarse grain it and you have a situation such that the two particle chains are coordinated. And that's what's required to get to Minkowski. And that basically gives you an inertial frame. Their clocks are synchronized.
Yes.
Just one quick thing for the coordinated chains. Was there some condition that every node has to interact with the other chain? I mean, couldn't one particle have a bunch of nodes that are only connected to things in that particle, or is that not possible?
No, the nodes are defined by an active interaction. So each node either is the particle influencing something else or being influenced by something else.
Okay.
Unless you're coarse grain, which in the coarse grain picture, then more things can be going on.
Okay.
So I'll talk about the non-coarse grain. So she talked about what happens when you coarse grain and you get into coordination. I'm going to next talk about what happens when you don't coarse grain, which is very different. So. Very good. So I'm going to introduce the notion of the free particle. This is an abstraction, but it's one you learn about in quantum mechanics, right? So it shouldn't be too surprising. A free particle is a particle that influences, but is not influenced. So nobody influences it. So here we have our two observers. We're assuming they're coordinated. This particle here is influencing them. So I'm not drawing in all the coordination lines. So this particle here is influencing these two. And so we're going to take this and see what happens. We try to describe what the particle is doing. So here I'm going to do something a little bit different. Instead of focusing on intervals, you could quantify rates. I could talk about the rate at which the particle is influencing P or the rate at which it's influencing Q, right? There's two different ways to do things. So the rates and intervals are related by Fourier transforms. And I'm going to take n events along the particle chain and project them onto P, giving a delta P. I can take those same n events and project them onto delta Q, and I'll define the rates this way. So the rate at which it influences P is defined as this number n over 2 delta P, and similarly for the rate at which it influences Q. So these rates are really only consistent as coarse-grained averages. You have to average lots and lots of rates, lots and lots of events to get something like this. It turns out that the product of the rates is invariant because the delta P times delta Q is an invariant scalar, and that means that you can rewrite the rates this way, which you might imagine as to be analogous to mass squared equals E squared minus P squared. If this works out, then you can then imagine what mass would be. Mass is the product of the rates in this one-dimensional picture, and in this 1 plus 1 dimensional picture, the energy would be the average rate at which it influences, and the momentum would be the half difference. All right? So let's see if this holds any water. Beta we define as delta x over delta t, which is the anti-symmetric combination of delta p and delta q over the symmetric combination. We can write p over e as this anti-symmetric combination of rates over the symmetric combination. And going through all of this algebra, which isn't that much, you can show that delta p over e actually equals beta, which you would expect. The next thing you want to test is to make sure that transforming from one observer to another makes sense. And if you can do that, we know what the transformations are like. You have to multiply by these square root factors, which are related to the ways in which the observers are influencing each other. If we rewrite these energy and momentum in terms of the rates at which they're influencing the other observers, you can easily show that you get the Lorentz transform versions, and you can show how energy and momentum would change in this picture. So with this picture gives you a natural way of thinking about energy and momentum as the rates at which it influences the particles would influence observers. Now this is kind of nice because position, which is an interval, and momentum, which is a rate, are going to be Fourier transform duals. time, which is an interval, and energy, which is a rate, is also going to go for you to transform duals. And now you have some explanation as to why you have something like complementarity. So momentum and energy only make sense as long-term averages. They cannot be defined in an event. And an important point is that the particle does not possess position, it does not possess momentum, it does not possess energy. These are all quantities that describe the behavior of the particle relative to an observer. So it's all observer-based. Pris's position is relative to me, his energy is relative to me. If you come running across the room, you're going to look at him and he'll have a different energy and a different momentum. And this is what this picture actually gives you. So one of the important ideas in quantum mechanics is this idea of information isolation. And you can see that this actually comes out here as well. If you have a particle that's influencing our observers, here P is being influenced at event P1 and P3, Q is being influenced at event Q2, Q4, and Q5. And all these observers know, really, is that they're being influenced. Okay? And they might get together and compare notes and say, what is that particle pi doing? And P says, well, I don't know, I was influenced at P1 and P3. And Q says, well, I was influenced at Q2, Q4, and Q5. Well, let's make some inferences about what the particle is doing. The problem is that these are on different chains in the partially ordered set, so I can order P1 with respect to P3. I can't order P1 with respect to Q2. So if I'm going to make inferences about what the particle is doing, I have to consider all possible orderings of these P's and Q's. So here's a simpler example with just 3 of them. Here in this case, this particle influenced P at P0 and P1, influenced Q at Q1. And if I consider all possible orderings, the particle could have done something like this, where it first influenced P0, then influenced P1, then influenced Q1. It could have first influenced P0, then Q1, and then P1. Or it could have first influenced Q1, P0, and P1. What's interesting about this, if you then go through and use their formulae to compute distances, these are equivalent to paths through space-time. So if you're going to make inferences about what the particle is doing, what do you have to do? You have to consider that the particle took all possible paths through space-time. There is no space-time. You're just making inferences about events that can't be ordered.
So are P and Q coordinated?
P and Q are coordinated, yep. But you still can't tell whether it influenced P first or Q first. Measuring does something very interesting. Here we have our particle that was free, but now I'm going to have P influence the particle. And this allows me to partially order some of these events. So now I know that P1 came before P2, and P2 comes before Q2. And this ability to partially order actually gives you information about what the particle is doing. And so we haven't fully explored the consequences of this, but it basically breaks the information isolation and allows you to learn something about the particle. Another interesting thing that happens is you see that these free particles, basically, if you look at an interval, an interval between 2 successive events in the particle chain, and you compute this factor beta, which is like the velocity, you will see that you can only get values of +1 or -1. So this reproduces behavior known as Zinnern-Bavagin, which Schrödinger found, which was predicted by Schrödinger by looking at the speed eigenvalues of the Dirac equation. So the Dirac equation says that the particle, if you're going to measure instantaneous speed, you're only going to get values of +and -1. And this is exactly what you get here in this picture. So what's interesting about this is when you put it all together, you can show that this exactly gives you the Feynman checkerboard model of the electron. And I don't know if I'll have time, but at the end I can walk through the derivation where you actually compute the quantum amplitudes. So this is actually a problem in Feynman and Hibbs' book, where the electron is described as making these bishop moves on a chessboard. at the speed of light. And Feynman gives a little rule for the quantum amplitudes. If you're going to go straight, you give it an amplitude of epsilon. If it makes a zigzag, you give it an amplitude of I epsilon. And then the problem is derive the Dirac equation from this. And we can actually also derive the amplitudes this way. So we can go a bit further. So I'm going to have another intermission and introduce James.
When the particle receives influence, well, it would make sense if influence were related to force, because influence affects the rates, and momentum is based on the rates. So let's see if that's true. So looking at the free particle again, if you look at the length along P between a first event of reception of influence and a last, it breaks up into subintervals. Between adjacent events, the length is k, which is the root m over n that was being shown earlier. As a result, the length between adjacent events on Q is 1 over k, and that's Lorentz invariant. So the length along P is the number of events along P times k, and the length along Q is the number of events along Q times 1 over k. Proper time is just half the number of events on the particle chain. So because the particle has no preference for influencing P over Q, the proper time is just equal to the number of events on P or the number of events on Q. So if you put these together, you can rewrite the increment in time as k plus 1 over k over 2 times d tau, and the increment in space as k minus 1 over k over 2 times d tau. So what happens when the particle receives influence? In this diagram, the particle pi is receiving influence from Q at events 2 and 6. And if you remember forward projection, you follow the influence lines to the least event on the observer that you can reach. So event 2 forward projects to 2p, 3p, and event 6 forward projects to p at 6p, 7p. So the interval along the particle chain, 2 to 6, forward projects to the interval on p, 2p, 3p, to 6p, 7p, which is 3 subintervals, each of length k. You can also back project, which is following influences back to the greatest event you can reach on an observer chain. So 2 through 6 on the particle chain back projects to 2q through 6q on Q. That's 4 subintervals, each of length k sub naught. It's not 1 over k sub naught. You're back projecting here, not forward projecting to Q. So you have an interval on P and an interval on Q. By coordination, those two intervals have to equal each other. So you get that 3k equals 4k naught. K naught has to be the original value of k because you're back projecting. K is the new value of k. So in this way, k changes due to reception of influence. If you call NP1 the number of events between reception events on the particle chain, so here NP1 is 3, then in general, you get that NP1 times k equals NP1 plus 1 times k sub naught. And that's how k changes due to reception of influence from Q. So k will also change due to reception of influence from P. And let's calculate how that works. So if you define for convenience the rates of influence from Q and from P, and the difference between them, R, then you can write the change in k as parts from Q and P, the first from Q and the second due to influence from P. At this point, we're restricting our attention to situations in which k is continuous. It's not an assumption, we're just restricting our attention. And the kind of continuity here is akin to the continuum hypothesis in fluid dynamics. So your differential amount is a large number of events, but that large number of events is still much smaller than the smallest measurable amount, so it's differential. Using continuity, you get that dk is this expression, and by the same arguments, you get that d1 over k is this expression. So dk and d1 over k are connected by calculus, and if we write down that relation, we get the first equation here. If you solve by sending r q bar to 0, for example, you get that the unknown function of r p bar is just minus r p bar k. And again, with r being the difference between the rates, you get that dk is rk d tau, which gives you that d1 over k is minus r1 over k d tau. And if you just divide through this by d tau, you get that dk d tau equals rk. So that's the way that k changes due to reception of influence. So let's solve that in the case when r is constant. Well, the solution is k equal to an exponential, which you can write as e to the r tau plus phi naught. If you plug that into dt and dx, you get hyperbolic cosine and hyperbolic sine times d tau. If you integrate that over d tau, then you get that time is hyperbolic sine and x is hyperbolic cosine, so that the velocity is hyperbolic tangent. Those are the results of special relativity for constant rate of acceleration, where phi naught is the initial rapidity, and r can be identified with the acceleration in the momentarily co-moving reference frame. So reception of influence produces a change that agrees with special relativity in the case of constant acceleration. You can also derive Newton's second law very easily. You can write the momentum as 1/2 k minus 1 over k. So if you take dp and plug in the expressions for dk and d1 over k, you get that this is dp. If you divide through by d tau, you get dp d tau is equal to this, which is 1, which is the mass in lattice units, times 1/2 k plus 1 over k, which is dt d tau, or gamma, times r. So you get dp d tau is m gamma r, which is Newton's second law in relativity, again with r being the acceleration. And you can also take differentials of d tau and dx. For example, d d tau has two terms just by the product rule in calculus. First term, you have k changing and the n's constant. Second term, which is what I've been talking about, second term you have k fixed and the n's changing. That's different, so you have to treat it differently. But if you do that and continue to restrict your attention to the continuous case, so that you can drop terms second order in differential amounts, you wind up with these equations, also after rewriting things in terms of quantities independent of the particle. These equations are, of course, of the form of the geodesic equations in general relativity in 1 plus 1 dimensions, with a particular relation among the Christoffel symbols, which is a coordinate condition. And this is still being worked on. So, any questions for clarification? Yes.
So having the influence come from the particle back to the observers, that makes the particle accelerate? I'm kind of confused what's sort of happening. Or is that now make it follow some kind of curved geodesic?
Well, when you receive the influence, two things happen. If you remember for the geodesic equations, those two terms, the first term had k changing. And that k changes because these lengths along p and q have to match. that gives rise to the acceleration that agreed with special relativity. And then if you hold k fixed and allow the ends to change, and again apply coordination, you get changes which, together with the first kind of change, gives you the geodesic equation. So receiving influence accelerates you in a way that gives geodesic equations. Is that your question?
Yes, I'm still going back to what I was thinking, sort of imagining embedding this into Minkowski space-time or something. And now I'm wondering why the particle is suddenly sort of... Is there a force on it from something?
Well, if the particle's at rest with respect to the observers, which would happen if it's influencing both equally, right? Then being influenced would ruin that. So basically, ruining that changes its state of rest to motion.
So these influences aren't just like structure; they're actual stuff happening along them or something. They're actually.
Not necessarily.
But I'm having a hard.
It doesn't actually
Well, then
matter.
how would it move in a curved?
Yeah, what's making it not move in a straight line?
It's the way that the observers, the observers are the observers are just trying to quantify what the particles doing, right? What's going on, and it turns out that the only consistent way to quantify it leads to acceleration.
I'm beginning to see why you put that quotation at the beginning.
It's not actually moving. It's not moving. There's no motion. There's no space. They're just. This is the only way that the observers could quantify it. It's very. Yeah, it's very strange.
So, okay, the forces aren't. I should take that seriously, but the forces aren't sort of fundamental.
Yeah. Oh no. Yeah. Well, the influence is this influence.
What
Whatever
you
it
see
is.
of
I mean, it
it
could be a
is really
computer
what's-
simulation for all you know. If the observers were quantifying it in a computer simulation, they get the same answers. So it doesn't really matter what the influence is. It turns out it's just interesting.
Can I ask a related question? So, would a good way to think about this being that if we're in Minkowski spacetime, the inertial paths maximize the time-like interval, and what's happening here when we've got acceleration is all the coordinated observers, or the observers that were coordinated, are now saying that the time-like interval is reduced. Is that?
The time-like influence, I'm sorry?
The time-like intervals reduced.
Yes. Yeah. The intervals along the observer chains are equal, but they're different due. They change due to reception of influence. I think that's fair to say.
The proper time goes down.
So okay. So if I put it in operational terms, I'd be saying, well, these observers are just measuring a shorter of the.
Sure. That's another way to look at it. Just really what you need to do correctly, right? That's sort of the key points. All right, so I'm going to go back to the quantum mechanics part of it. So I showed you briefly how this free particle basically experiences sort of a akin in 1 + 1 dimensions. And that this gives rise to the same picture that you have for the checkerboard model of the electron. Now, if you look at it this way, as the particle, so you can imagine these two pictures are very different. So imagine you have the particle in this situation where it can influence either of these guys. It could be that the particle came in from this direction like this, which means, and coming in from this direction, what I mean by that is it influenced P, right? And coming in from this direction, what I really mean by that is it influenced Q. So I could have the initial state where first it influenced P, or previously had influenced P, or previously had influenced Q. And in the next step, it may influence Q, and then may influence P, or it could influence P and then influence Q. Right?
These are not positional momentum.
You can draw this in terms of position and time, because we can change the delta P's and delta Q's to delta T's and delta X's. Or we can talk about it in terms of whether the particle influences Q and then influences P.
So Q and P are these lines again?
So what I've done is,
Okay, right.
yeah, so what I've
just
done
these
is,
things.
yeah, this is half of the diamond here, right? So this corner here, what's happening is it's influencing Q. But if I express it in terms of delta t's and delta x's, I can draw it this way. Right? So you can think of it in space and time, or you can think of it in terms of the partially ordered set as to who it's influencing, which of the two observers it's influencing. So what I've done is I've labeled this suggestive vector through space-time with a Q to indicate that this is what happens when it influences Q. This is what happens when it influences Q. So this will move to go from this initial state to this initial state in terms of, here I've written R and T, it should be X and T, but and X and T plus delta T. It can happen by influencing P and then Q, or it could happen by influencing Q and then P. And because I can't order P and Q influences, I have to consider both of making inferences. So here, so we're going to use complex numbers to compute our probabilities. It takes a little bit of work to get here. There's 2 papers that I've written with Philip Royal that derive using pairs of numbers and showing that you can derive the Feynman formalism for complex amplitudes from basic symmetries. And so I'm just going to employ this here.
Okay. Is that circle supposed to be coming out of the plane of the ball of the screen? Okay.
No, it's just.
It's in the plane.
Yeah.
Okay.
So this is actually an uncertain. This is an uncertain sequence order. So it's a coarse-grained measurement in terms of the quantum measurement sequences. So this refers to actually another paper in another lecture. So the initial state is uncertain, and I have to take that into account. So I need a complex number to handle the fact that it could have previously influenced P or could have previously influenced Q. So I'm going to do that. So here's a complex number to indicate that I previously influenced P. There's the complex number to indicate that I previously influenced Q. And now I'm going to take this 2-component object, which accounts for this uncertainty, and now propagate it using basically, you can show that you have to use matrices to handle the PQs and the Q moves, or the P influences and the Q influences. So basically I can operate on this initial object. If I had previously influenced P, I'm basically going to operate on it with influencing Q and then influencing P again. Here, this path here indicates that I previously influenced Q, and now I'm going to influence P and then Q. Or I could have previously influenced P, then influenced Q, and then P. Or I could have previously influenced Q, and then Q again, and then P. So there's 4 possibilities. And you can show by symmetries that the matrices have to have this form. So I can write these matrix equations this way. So P operating on this initial pair of complex numbers gives me something like this. Q operating on this gives me that. And now I must have that, since my conditions are that I started at some in this state and I'm going to end in this state, either this had to happen or that had to happen. So those 2 probabilities have to sum to 1. And you can rewrite this in terms of these complex numbers this way, using the Born rule. That has to equal 1. This gives me a condition on these matrices, which allows me to solve for those factors x and y. And so basically gives me this equation here. So this implies that x complex conjugate times x plus y complex conjugate times y has to be 1, and then the other terms have to sum to 0. If I write them in polar form, it's a little nicer. Basically, I have that the amplitudes have to sum to 1. This is the unitarity, and the phases have to sum to 0. So the relative phase angle must be either pi over 2 or 3 pi over 2. Again, it's obvious you need complex numbers to do this. And so I'm just going to consider the case where these are equal. And we've been investigating as to how this changes if the particle has some non-zero average beta. So choosing x to be real, which you can do, is you put some arbitrariness there. Basically, this is your matrix for P, this is your matrix for Q. And now you can see that if I previously influence P and influence P again, I multiply by a real number. If I started with Q and then influenced by P, make a reversal, I have to multiply by that by a real number times I. So this is the factor of I that you get on reversal that comes from Feynman's prescription for the quantum amplitudes. So we go a bit further than Feynman and Hibbs, we actually derive the amplitudes, which is kind of nice.
But didn't that come from assuming setting A equal to B?
I'm sorry?
Didn't that come from setting A equal to B?
No. If you change A and B, it doesn't change the I's. You still get there. What ends up happening?
You get cosine theta on the diagonal and I sine theta on the off theta.
So basically, you can then show, and we have a derivation for this as well. I'm not going to go into it, but you can actually get to the Dirac equation this way. So in one sense, when we coarse-grain the picture, you can retrieve elements related to space and time. But if you go down to the microscopic picture here of chains representing particles that are directly influencing each other, you then get behavior like fermions. So these things act like fermions. So the two are getting along happily, which is promising. So the simple theory is based on only the idea that there's things which influence one another in a transitive fashion. To get the Minkowski metric, you have to have this idea. You have to be coarse-grained, and you have to have this idea of coordination, which basically sets up an inertial frame. But this gives you quantitative descriptions of emergent space-time motion, courses in some aspects of fermion physics. One of the key ideas is this idea of chain projection onto observer change. So the theory is necessarily observer-dependent, but it's objective in the sense that this idea of consistency means that each observer is going to agree on the same laws. So the post-set events are quantified by this chain projection in conjunction with this concept of consistent quantification. And it's based on fundamental symmetries like associativity and commutivity, things like this, not transformation laws. And most recently, we believe that we've come to understand that this theory only gives you 1 plus 1 and 3 plus 1 dimensions, and this is currently under investigation. It turns out that if you have 4 chains, you can show that you can project onto 4 chains, and this gives you a 3 plus 1 dimensional space. But if you try to do something with 5 or 6 chains, there are too many anti-symmetric combinations, and it's not closed anymore. So it's basically Galois theory rules out anything but 1 plus 1 and 3 plus 1, which is also promising.
Okay, we have about 12 minutes or so for questions.
Thanks. Fascinating stuff. I've just had a couple of questions. The first one, I'm really interested by this idea that you need some unknown internal states to define identity through time. So you could say a bit more about that. And the second question, you were just saying how you've got fermion physics. I mean, shouldn't we think that influence is happening through bosonic particles? To what extent have we got something that's working like QED? Is that something you hope to recover?
Yeah, no, those are both good questions. So the having, so to get a total order along the particle chain, somehow you have to order that, right? So the only way we've come up with is this notion that there has to be an internal state that's somehow affected by influence that you don't have access to.
So how does that allow you to total order?
So basically you can, let's see.
I mean, haven't you just put in by hand the fact that there's some motion of persistence?
Right.
Or is it doing more in there?
So the idea is that if you have a So let's say that this represents a state, right, and this represents another state. And so states are coupled by events, okay? And you can have events coupled by states. And so if the so you can argue that if the event is coupled by two states, so it's basically bounded by two states, you can then use that to order. You can then choose an order between those two states, and that allows you to get a total order there. And then it turns out you can either order it this way or that way, and then but that forces which way you order these two, so you can't have cycles, right? And so that allows you two freedom to you then have time reversal symmetry, basically.
Okay, thanks, James.
It forces you to do that. And then the other one's bosons, right?
Yeah.
Yeah, okay, so again, this is a theory not like the others, so we're not trying to make it like the others, but yeah, so these aren't mediated by anything. It's not, we don't imagine that there's a particle flying here now. Now we've thought about what can you do? What if you did try to quantify this as if it was some kind of particle, but we haven't gotten anywhere with that, so.
Yeah. I mean, that seems like quite a naive view of quite
Yeah, so we haven't been able to come up with anything like bosons this way. Yeah.
So by coarse-graining this particle-like story, you get out interference. But I mean, classically, if you coarse-grain a particle story, you're not going to get constructing each other's interference in this way. If under the following two assumptions, one of which you must be dropping. So one assumption you usually make classically is that there's one real history. You just don't know which one it was. And then the other assumption you typically make is to find the total probability. You add up the probabilities of all the histories for coarse-graining. So are you dropping one or both of those to get your interference? Is there one real history?
So the interference is coming from the complex numbers, right?
Okay.
Using complex amplitudes.
Well, but you coarse-grain to get that.
No, we didn't coarse-grain to get that.
Well, you coarse-grain to get multiple possibilities.
No, you just can't order the P events can't be ordered with respect to the Q events. So if they're going to make inferences, they have to consider all possible sequences.
Okay, so you have a bunch of possibilities. Is one of those basically you're not? So they all happen. They're all the same. They're just different.
Well, it doesn't matter for the observers.
So you're not saying one of them happens.
One of them. Well, according to the diagram, that there is one of them that happens.
Okay, so there is
but
one.
with respect to the observers don't actually know what happened.
Okay.
They can never know what happened. It's information.
But there is one real history.
Yeah.
And do you add probabilities of each of those histories?
No, you can't, because the observers are informationally isolated from the particle because they can't order each other's events.
Okay, so that you're not adding. Okay.
So this is about, the motivation for the sort of coarse graining. I mean, again, that seems like it's really key here. But why don't I just build a better detector? And,
No, you can with big quantum mechanics, right?
Coarse-graining only was, we used that only for the special relativity part. So then we dropped that because you can never have, in order to get this quantum mechanics part, you have to have these either being influenced or influenced the same. The only case that we could do that was just with the Newhouse leading and those transformations.
Yeah, the development went a little backwards, as always, right? So the development was such that we were playing with partially ordered sets and how to quantify them in general, and realized that if you projected onto observer chains and they were coordinated in this way, you would get something like Minkowski, and then showed we got Lorentz. Then the idea is, well, what does this actually mean? What kind of theory could you come up with? And we came up with this idea of things influencing each other directly, but then realized that at the fine resolution, the space-time doesn't work, right? So then how do the observers make inferences about the particles? And then we realized that gives you the Feynman Checkerboard model.
but that does go back to. So it isn't part of this that there's some sort of limit to it. I don't know, but it is compatible with all this that you can look closer and closer and closer as you like. I mean,
Yeah, if you look very close, the space-time ideas fall apart. The particles going the speed of light all the time. It's crazy. But for big things like you and me, it's coarse-grained, so space, there's
So the
time,
Dirac
energy.
equation is then one of the time. Okay, see, that is the case where the coarse-graining because it's back in special relativity. Okay. All right. I get it.
So then going back to David's comment that when you do coarse grain, you can end up destroying like the poset nature of these things. Do the derivations still hold when you showed like the derivation of the Minkowski length metric?
Yeah, because the assumption to get Minkowski is that the observers are coordinated.
Okay.
So the case you gave where it would kill the poset doesn't agree with that assumption, so.
Okay, please join me in thanking Kenyon Newshaw.